Hi, I hope you're all having a great conference. Thanks for attending this session. My name is Samir Raheja. I lead a team at NVIDIA working to accelerate batch data processing on GPUs. And I'm here to talk to you today about the RAPIDS accelerator for Apache Spark, to talk about how you can accelerate your Spark workloads on AWS EMR and AWS EC2 instances. So let's dive right in. So in this talk, I'm going to give an overview of the challenges of big data processing today and how the RAPIDS accelerator for Apache Spark addresses some of those challenges. I'll talk a little bit about the performance and cost savings that you can get using the RAPIDS accelerator for Apache Spark. I will also talk about how do you choose from the thousands of Spark jobs that you may be running, which ones are the best suited to be running on GPUs? And then I'll talk a little bit about some next steps and hope you guys can get started. So to dive in, anybody who's been involved in data processing for the last few decades knows that data has grown exponentially year over year. With the growth of AI and ML, that's really fueled the need for high quality data at low latency. And data growth has come from so many different places. It started with the internet, went through growth with consumer handheld devices. Now we're growing with Internet of Things, both consumer and industrial Internet of Things devices. Just to give some statistics, earlier this year, Apple said there are 2.2 billion active Apple devices in the world today. And Android said there are 3 billion active Android devices in the world as of 3 years ago. So it's an amazing number of devices that are throwing off data, and enterprises are trying to process petabytes of data. So how do you do that? How do you handle that incredible increase in growth of data? One way of doing data processing is with horizontally scalable data systems like Apache Spark. You can add more compute to your clusters to handle the increase in growth in data. You can scale horizontally, add more CPUs in your AWS clusters. Another way to handle the growth in data is you could downsample your data. So there are situations where you've got tons of data coming in and you want to use that data for reporting or modeling. You need to get those reports or models out within a certain SLA or time period. How do you do that? One way, if you want to keep within your budget, maybe to downsample the data, you get less accurate reports or less accurate models. A third way is, well, just keep the size of your cluster the same and let the time that it takes to process the data, to get those updated models or to get those updated reports just take longer. Well, I propose there's a better way. And with the slowdown in Moore's law, we need a different way of approaching large-scale compute. And one of those ways is with accelerators or NVIDIA GPUs. For Apache Spark, we have worked on Apache Spark 3 to enable batch data processing on GPUs. Apache Spark 3 has some additional new functionalities that allow us to do processing on GPUs. The first of those is that Apache Spark 3 has resource-aware scheduling. So since the release of Apache Spark 3, you could schedule a task on a CPU, or you could schedule a task on an accelerator like a GPU. Apache Spark 3 also has the ability to do columnar data processing. So when we're doing ETL or OLAP processing and we're processing very large chunks of data, throwing large amounts of data at a parallel processing engine like a GPU can be very efficient. The third thing that Apache Spark 3 brings to the table is the ability to have plugins. The RAPIDS accelerator for Apache Spark is a plugin to Apache Spark that works with different Apache Spark distributions, including the ones you see here. So we can plug into Apache Spark, we can plug into Databricks, or we are embedded with AWS EMR. We can also work on any number of different Apache Spark distributions. From a user perspective, as long as you are running with SQL or on any data frame type of operation, say using PySpark, Java, Scala, R, we can accelerate those jobs. The jobs can be scheduled using the Apache standalone scheduler, the Kubernetes scheduler, or the Yarn scheduler on EMR. So we work with EMR on Yarn, we work with EMR on EKS. To go into a little bit more detail about how this works and what's happening, from a user perspective, again, there's no code change required. A user needs to configure their Spark job to use the Apache Spark plugin, but their SQL and data frame operations remain the same. We use the existing Spark core to schedule jobs and tasks on a cluster of nodes. In this case, we may schedule it on a cluster of GPU nodes. So when the RAPIDS Spark plugin is enabled, if an operation has been GPU enabled, we will call out through a JNI binding to an open source library called RAPIDS. And we use the RAPIDS CUDA data frame libraries to make CUDA calls to the GPU. For a user, if there is an operation that's not GPU accelerated, they don't need to worry about it. We fall back seamlessly to the CPU. To look in a little more detail at what's happening, here's an example SQL query or PySpark data frame application. Spark takes this data frame application, converts it to a logical plan, optimizes the logical plan, converts it to a physical plan. It then runs the physical plan on the CPU normally by running the execs and operators on the CPU, and returns the row-based data. When running with the RAPIDS Spark plugin on a GPU cluster, that CPU physical plan is replaced with a GPU physical plan. So those CPU execs and operators are replaced with GPU execs and operators that are running on the GPU. Again, this is downstream from the user. They don't need to worry about making any code changes. Everything is happening for them. So how does this actually perform? So let's take a quick look at a benchmark. We run a benchmark called NDS, the NVIDIA Decision Support Benchmark. This is a derivation of the TPCDS benchmark, which all of us in the data community know and love. It's a benchmark of 100 SQL queries. This is not exactly the benchmark in the sense that there are very subtle changes for the Spark SQL syntax in terms of single quotes, double quotes, but we publish the benchmark in our GitHub so that you can try this and replicate it yourself. And we also want to show you the configurations so that you can try this for yourself. There are a couple of specific configurations for the GPU. So Spark configurations for scheduling tasks on the GPU. We have some optimizations for I/O because we want to keep the GPU and CPU as busy as possible. And in order to do that, we have a RAPIDS Shuffle Manager, so we can overlap I/O and compute between the CPU and GPU. And then a user needs to call out and enable the Spark RAPIDS plugin and set the number of concurrent tasks that will run on the GPU. For this benchmark, we're using, we'll start with an AWS EC2 cluster. And running with Parquet data at scale factor 3000, with data stored on S3 buckets running Spark 351. We have two clusters to compare. A CPU cluster of 8 M7GD 8x large Graviton instances on EC2 versus 8 G6 8x large instances. You notice the G6 are the L4 GPUs, and we chose these two instance types because they're very similar. Same number of CPU cores, same number of host memory, very similar in terms of networking, storage, but there is a cost increase for the GPU. So in order to make this worthwhile, we have to get performance that overcomes that cost differential. So if we look at all 100 queries on this benchmark, we see that the performance on the GPU is always better than the performance versus the CPU, with some performance being up to 9x faster. And the average speed up is 4.8 with a cost savings of 72%. So this is on EC2. Let's take a quick look on the EMR cluster. So a very similar setup, the same exact configurations using EMR 7.3. In this case, adding the driver nodes for the EMR cluster and updating the costs for EMR. EMR adds the software cost over there. So in this case, we are still faster with the GPU on the EMR cluster. The average speed up of 1.3x and a cost savings of 14%, with the fastest query being up to 3.5x faster. Now there are a couple of queries that are slower. And what's happening here is that there are some optimizations in EMR that we don't recognize, so we fall back seamlessly to the CPU. So we're not getting as much benefit. We are working closely with the EMR team to embed the plugin more closely with EMR so that you can get the full benefit of both the EMR Spark speedup and the RAPIDS accelerator speedup. But then this also leads to the question, so I've got 100 queries here. Which ones of these should I actually run on the GPU? Because you may be running thousands of queries in your organization. So let's take a look at an example that the AWS Financial Services Solution Architect team investigated. Transaction fraud is a huge issue in the financial industry. The largest, it accounts for billions of dollars in lost revenues. The largest credit card transaction processors process hundreds of billions of transactions per year. So when we're talking about exponential data growth, this is an example where there are hundreds of billions of transactions, and how do they end up processing all of this data to identify fraud? What they do is they do time series analysis on the data, looking at sliding scale windows of small increments of time and like minutes, 15 minutes, hours, hours during the day, days, weeks, months, to identify this persistent problem in the industry. So what we did was we took this particular use case and we ran it on AWS EMR using the RAPIDS Spark plugin, with and without the RAPIDS Spark plugin, to compare what the performance would be. So in this case, we use a slightly different cluster shape, the 12 R6G 4x large instances versus 12 G6 4x large instances. And you can see here the cost is even more significant. 65% more cost for the GPU cluster. Again, data stored on S3. Otherwise, the node types are relatively similar. And what we see is, in this benchmark, there's a 14x speedup when running this set of SQL operations for windowing time series analysis on the GPU, because it can be massively parallelized. And users would get an 87% cost savings. Now, in the previous benchmarks I showed, we were running with 3 terabytes of data. Here, we only ran with a 120 gigabyte data set. The CPU time in this 12 node cluster took 10 2.5 hours. The GPU cluster took 3/4 of an hour. We couldn't even scale this up larger to do a comparison because it would have cost too much to run on the CPU cluster. So then the question is, okay, how do I identify these kinds of jobs in my environment? What we've done is we've created a tool to help you identify the jobs that are best suited for you that will evaluate your existing Spark event logs. So this is an open source tool, just like the RAPIDS Spark plugin. It's available on the Python package installation site. You can pip install Spark RAPIDS user tools and run a command, Spark RAPIDS qualification, select platform EMR, and point it at your S3 bucket that has your Spark event logs. And we'll make a recommendation. We'll figure out what are the top qualified candidates to run on a GPU cluster. We'll make recommendations on the cluster shape. And we do this based on a model that we created. We've got a lot more details that we will print out for you in different folders and files that'll give you information on how you can configure your jobs, how you can tune your jobs, if you want to dive into that. To make this even easier, we have a notebook that you can download and run against your EMR cluster. So you can run this notebook inside of the EMR workspace. This will download the Spark RAPIDS tools for you. You set a few settings here to point this at your S3 bucket path to pointed to your logs. Provide an output path for the results, and we will show you what applications are recommended to try on the GPU. So with this, we believe that it is possible to reduce costs, even with the incredible increase in data growth that's happened over the past few years and is going to keep happening over the next few years. You can accelerate your Spark jobs and get cost savings at the same time by using GPU clusters on the cloud with AWS, EMR, and EC2 instances, or even with other Spark distributions like Databricks on AWS. This will allow you to process all of your data at high fidelity and within your SLAs. For more information, I encourage you to try this yourself. There are some QR codes here that you can use to go to a couple of different pages. We've got documentation, extensive documentation on how to use the RAPIDS Spark plugin. There is documentation in the AWS website on how to use the NVIDIA Spark RAPIDS plugin in EMR. There are instructions there on how to bootstrap your cluster with our plugin. And there is a link for downloading the RAPIDS Spark user tools. I would also encourage you to stop by our booth, booth 1620, and talk to us or talk to some of our Inception partners that are there. And if you have any questions, I'll be here after the session. So, thank you very much.